Well, now we've seen neurons, layers, columns, regions, networks, and the entire cortex disambiguate our host of sensations by using massive parallelization to produce a collection of objects relative to ourselves and to one another. But what about ourselves in relation to the space we occupy? How do we scale up perception from the self to objects to the environment? Well, using the same common cortical algorithm we've used already.
So let's look at this another video here and see how this works. This is a very interesting one. This is the grid cell finding from 2010. Now, there's a single neuron here in the entorhinal cortex. And the entorhinal cortex is the part of your hippocampus that is you. In other words, it's your location and orientation. Not other things, it's you in relation to the world. And about now you can see some patterns starting to form here. And this is what makes a grid cell a grid cell. Now, this pattern is actually telling us distance. So there's a distance x size of the animal's body, and there's another distance x size of the animal's body. And we end up with this pattern. This pattern is a set of triangles organized into hexagons. So a triangle is, where's my body, and I can turn right and left. It's really that simple. And another body. So we're actually calculating and counting distances as we move along. And this is fascinating that this is being done in a very old part of the brain in very great detail. And it shows how we are physically measuring space by physical interaction
With it.
and we're remembering it.
Now you'll notice that we see equilateral triangles, and that those triangles combine into well-ordered hexagons. And oddly enough, some researchers noticed that as well. And it turns out that it's because the spaces they're testing the rats in are regularly shaped in round or square. But if the spaces are instead irregular, meaning narrow or oddly shaped, we'll see that the triangles and hexagons distort to suit the space while maintaining approximately the same area within each triangle, the area the physical body of the rat can pivot within. So we don't really just sort of count, there's no counter in us of like there's one body space, two body space, three body spaces, or 3 paces, 4 paces, 5 paces, etc. but we have this rough approximation of the distance to something by our mere experience of it. And we assemble these maps of the world so that we can recognize, regardless of which direction we're facing, the same space. So this is why, for example, we might go follow a path. We'll recognize the path going the same direction, but if we reverse the direction, we may not recognize the same path as the same space unless there are other indicators like objects or reference points within it. Now, we assemble these grid positions into reference points no matter what our orientation. So in the left illustration, you can see a collection of loops, and they're sort of average into a roughly circular shape in the right illustration. And you can see how multiple overlapping traversals of that space from different directions produce a distribution that is roughly a circle within a hexagon, or a center point within boundaries. Now, this isn't accidental, it's evolution making use of efficiency. A hexagon is an extremely efficient combination of triangles that allows the description of spatial distance and relative position in all directions at a uniform scale. Now, it's very countable, very estimable. Now, and as we've seen in this collection of colored circles, it's the minimum number of points that we need to overlap in order to produce commensurability or fit between orientations. I mean, evolution is brilliantly efficient, and it's this elegant and efficient way of storing and aligning many dimensions of fragmentary geometries using massive parallelization of very simple stimuli.
Likewise, if we watch this video, which is similar, this is location cell. And you can see this rat following along a little channel here. I can't remember if it's eating food or not, but you can see by the integration of the poor rat with its location cells that it's developing a map of the world around it. He's off sniffing the side now. And that different combinations are being drawn based on his location. So he's developing a map of the world that he can sense, just like you and I feel texture, we can feel space and time and distance. So when I'm emphasizing geometry, there's a reason for it. It's that we're not processing spatial relations separately from our other senses, but instead what's happening is we are processing everything as spatial relations. So this is what the lovely rat did, is he developed unique patterns, shown as colors here, patterns for every location in here, and that's how he will remember those locations. So we have two sort of things I've tried to show you here, which work by the same process in the neurons in the cortex. In other words, the columns are trying to define relative position. In other words, what is the relative position of the things I am sensing to one another so that I can construct an object. We are in the we are in the grid cell, which is what's my distance from any given reference point, and a place cell, which is where am I, what unique place am I building, and we're building them out of very sparse activations. So the same process from touch to body orientation to head direction to location. In other words, the same process is happening at every level of the body, and it's cumulatively building these overlapping maps of the world that we experience intuitively as one.
So we have three ways of identifying our location. We can do it by object recognition, which we've seen so far, and that will hopefully help us find it by association. We have place location, as we see now. We can build a map of a place, and we have location reference so that we can find locations. So we have multiple means in competition with each one another of identifying where we are in space. Now, hopefully, I'm succeeding at getting across to you this framework of using multiple transparencies consisting of fragments of the world we're perceiving, using simultaneity in time and grid cells at different scales to find commensurability in time and space, with successful compositions surviving and getting through to our experience.
So we disambiguate a million visual, 30K auditory. I'm sorry I didn't mention that earlier, but we have about a million visual neurons, 30,000 auditory neurons, neurons, not inputs, and 1 million bodily nerve cells. In other words, there's 1 million from our eyes, 1 million from our body, and 30K from our ears. And we put that into relations, then fragments, then models, then entities and maps, and environments, and then finally into simulations. And we feel that geometry. Just like we feel temperature. We don't think of it that way, but we can take great examples of people who and give them blindfolds and watch what they do, and they will, very much like the rat, eventually develop a model. We're just so dependent on vision. It's so powerful that we take our vision as primary instead of our vision contributing to our ability to act and plan routes in three-dimensional space with the complex bodies that we have. So our sixth sense really is space. Sensory motor combination, location, orientation, offset, sequence, prediction, scale, and we turn fragments, models, entities, maps into simulations. And honestly, logic is our seventh sense, and as we go through, when we get to the grammars, you're going to see why I'm making such a big deal about this idea of geometry and our and the way we perceive the world subconsciously, according to the same kind of things we find in our analysis of that specialty we call geometry. So we're going to see geometry show up in our language the same way we've just strangely seen triangles and hexagons and distances show up in our sense perception, and just as we've strangely seen that our sensory world is always calculating and combining location and time and space along with everything, even the curve of a coffee cup. And we don't think of these things as geometry, but they are. They're stored as positional relations. And they're organized by predictions into reference frames, entities. And there's a lot of them. I mean, everything learns a model of something up there. And we are able to combine these prediction models into various pieces. Now, I'm not going to go into this. I love this reconstructed microcircuit of the brain. This is a wonderful example of it. And the math below it, you can pause this and read this if you'd like to. This is me trying to put in a little explanatory power for later. But the process is pretty interesting. We continuously in time take many inputs using massive parallelization, discovering constant relations, organize them into dimensions, into ever-expanding associations across limited periods of time, producing ever-expanding predictions from which we choose actions.